the concentration of the reactants will be the maximum, and therefore the rate also will be maximum. Let us plot the concentrations of the reactants and the products. Say here there is a time. Time is plotted along the x-axis. And here you can plot the concentration of the reactant or product. At the beginning, so this is the reaction. Reactant R reversibly giving product P. Reversibly giving. You read the double head arrow as reversibly giving. Reversibly giving. So R reversibly giving P, where R is the reactant and P is the product. Okay. At the beginning stage, there is only the reactant. And so the concentration of the reactant will be the maximum. And when the reaction progresses, the concentration of the reactant, it becomes say lower and lower, say it goes like this. When time goes on, the concentration of the reactant says the concentration of the reactant. Square bracket R is to be read as concentration of R. So concentration of the reactant decreases like this. On the other hand, say after some time, product is formed. And when the product is formed, the backward reaction, the reverse reaction begins. And time goes on. When time goes on, the concentration of the product increases. More and more product will be formed. And therefore, the concentration of the product will be increased. Say at the beginning, concentration of the product will be 0. And when time goes on, say the concentration of the product increases. And after the equilibrium, say after the equilibrium, we can draw the sketch again, say like this. Okay. So in the beginning, for the reactants, the concentration time graph will be like this. The concentration decreases with the time. But for the product, the concentration time graph will be like this. The concentration increases. When equilibrium is reached, you can see that the concentration remains the same. Concentration of the reactant or the product, it remains the same, and this is at equilibrium. This is the equilibrium condition. At equilibrium, see the concentration of the product remains a constant. Similarly, the concentration of the reactant that also remains a constant. You can plot the rate also. If the rate is plotted against time, what will be the nature of the graph obtained? Here you can plot the rate, and here you have the time. Say at the beginning, the concentration of the reactant is the maximum, and so the rate also will be maximum at the beginning stage. When time goes on, the concentration of the reactant decreases, and therefore the rate of the reaction, forward reaction, that also decreases. See, after some time, the rate of the forward reaction, say, decreases. See, like this. This is for the forward reaction, forward. But you take the backward reaction or the reverse reaction. When time goes on, the concentration of the product increases, and therefore the rate also increases with time. And after some time, when equilibrium is attained, say the rate of the backward reaction or the rate of the reverse reaction remains the same. Say at this point, this is the meeting point. At this point, both the rates are equal. Rate of the forward reaction decreases slowly, while the rate of the reverse reaction, backward reaction, increases slowly. And at a certain moment, the rates of the forward and backward reactions will become equal. And this is the equilibrium position. So the graphs will be like this. I repeat, when the rate is proportional to concentration, make it clear that the rate of a reaction is proportional to concentration. In the reversible reaction, at the beginning, there is only the reactant. So the concentration of the reactant R will be the maximum at the beginning. And when the reaction progresses, the concentration of the reactant decreases, and you'll be getting, say, a graph shown here. On the other hand, when the reaction progresses, the concentration of the product increases. And the nature of the graph, say, will be as shown here. At a certain time, certain position, the rates will be remaining, say, a constant. Say, this is the rate of the concentration, not rate, the concentration. So this is the concentration of the reactant. It remains the same. Say, concentration of the reactant remains same at equilibrium. Similarly, the concentration of the product, that also remains the same at our equilibrium. There is no change in the concentrations of the products and reactants. So remember that it does not mean that the concentration of the reactant is equal to the concentration of the product. It is not, that is not the meaning. Don't think that concentration of the reactant is equal to concentration of the product. No, it is not what I have meant. I say that concentration at equilibrium, the concentration of the reactant remains the same. Whatever be the value, it remains the same. Similarly, the concentration of the product, that also remains the same, whatever be the value. Similarly, you take the rate. At the beginning, the rate of the forward reaction will be the maximum. And when time goes on, the rate of the forward reaction decreases. But the rate of the reverse reaction, it slowly increases when time goes on. And finally, at a certain point, the rates of the forward and backward reactions will become the same. And that is the equilibrium point. And at that point, the concentrations of the reactants and the products will remain unchanged. It does not mean that the values are equal. Next point is equilibrium constants. We have to study another definition, equilibrium constants. Equilibrium constants. We have to see two equilibrium constants, two types of equilibrium constants. Let us take, say, a reversible reaction, say R, reversibly giving a product P. Now you take the ratio of the concentrations of the products and the reactants. Ratio between the concentration of the product and the concentration of the reactant. In the numerator, the concentration of the product, right hand side. In the denominator, concentration of the reactant, the left hand side. Then you will get, say, a value, a constant K. So K is equal to concentration of the product, P, right hand side, at equilibrium, by concentration of the reactant, that is R at equilibrium. Say square bracket P, that is the equilibrium concentration of the product, not the concentration at the beginning, not the concentration at the final stage. It is the concentration at equilibrium. Concentration at equilibrium. So square bracket P, concentration of the product P at equilibrium. Now square bracket R, that is concentration of the reactant at equilibrium, not in the beginning stage, at equilibrium. Both the concentration terms are the concentration terms at equilibrium. Equilibrium concentration of the product by equilibrium concentration of the reactant. And this ratio will be a constant. Why? Concentration of P, that is a constant. Concentration of R is also another constant. So a constant is divided by another constant. And therefore, this ratio is a constant. And this constant is called the equilibrium constant. Equilibrium constant. So, equilibrium constant is the ratio between the concentrations of the products and the concentration of the reactants. In the numerator, there is concentration of the product, right hand side concentration. In the denominator, there is concentration of the reactant, concentration on the left hand side. The reactant left hand side. And this ratio will be a constant, and that constant is called an equilibrium constant. Here we make use of the concentration terms, and therefore this constant is specifically mentioned as Kc. K for constant and C for concentration. So this is the equilibrium constant in terms of concentration terms. Equilibrium constant Kc, that is the equilibrium constant in terms of the concentrations of the products and reactants. Remember, products by reactants. Right hand side by left hand side. Right hand side by left hand side. And that ratio is called the equilibrium constant Kc. So I repeat, K for constant and C for concentration. So Kc is the ratio of the concentrations of the products and the reactants. The concentrations of the right hand side by concentrations of the left hand side. And that ratio is a constant. It is constant because at equilibrium, the concentrations will be constant. So the ratio also will be a constant. This is a simple case. Let us generalize this. Say, for example, AA plus BB reversibly giving CC plus DD, a general reaction. Here the reactants are A and B. A and B are the reactants. These are the reactants. We have two reactants here, A and B. A moles of capital A and B moles of capital B. And the products are C and D. Capital C and capital D. These are the products. C moles of small c moles of capital C and small d moles of capital D. Remember, capital A and capital B are the reactants. We have two reactants here. In the previous case, there was only one reactant, capital R, and there was only one product, capital P. Now, we are going to generalize this equation. That is, we have two reactants, capital A and capital B, and two products, capital C and capital D. Now, how can we express the equilibrium constant for this reaction? The equilibrium constant Kc is equal to right hand side by left hand side. You take the concentration of the product C, concentration of the product C, and you raise to the power of the coefficient small c, small c. Wherever there is plus, you put into that concentration of capital D raised to the power of small d divided by concentration of capital A, that is the reactant, raised to the power of small a into concentration of B raised to the power of small b. And this is also a constant. And this constant is also known as the equilibrium constant Kc. So equilibrium constant Kc may be defined like this. It is the ratio between the product of the concentrations of the products raised to the power of the coefficients to the product of the concentrations of the reactants raised to the power of the coefficients. A, B, C, D are the coefficients. Small a, small b, small c, small d. These are the coefficients of number of moles of each species. So equilibrium constant Kc is equal to concentration of capital C raised to small c into, wherever there is plus, you put into mark, into, you take the product, into concentration of capital D raised to small d by concentration of capital A raised to small a by concentration of capital B into capital B raised to small b, and that is called the equilibrium constant Kc, and C is for the concentration term. Okay, let us take some simple examples to illustrate this. Say, for example, you take the reaction between hydrogen gas and iodine gas, reversibly giving 2HI gas. You take a reaction like this. Here the reactants are hydrogen and iodine, and the product, that is HI. Now, how can you write the equilibrium constant Kc for this reaction? It's equal to, take the concentration of the product is HI. So concentration of HI raised to the power of the coefficient. The coefficient is number of moles, that is equal to 2 by concentration of H2. The coefficient is 1 H2. So you need not write it again. Concentration of H2 is the same as concentration of H2 raised to 1. Both are the same. Then wherever there is plus, you put into or into concentration of I2. Concentration of I2 raised to 1. Only one I2 raised to 1. And that is the equilibrium constant for the reaction. The equilibrium constant for this reaction is found to be the value. The value is found to be almost 57. The value Kc is equal to 57 at 700 Kelvin. You need not to study this by God. You study this one only. This one. So Kc for that reaction, that is equal to concentration of HI squared by concentration of H2 into concentration of I2. That's the equilibrium constant Kc for that reaction. And the value is 57 at 700 Kelvin. Okay. Now, if you reverse this reaction, say like this, Krishna, you reverse the reaction, not reverse the higher. Not reverse the higher, you reverse the reaction. So it is 2HI G, reversibly giving say H2G plus I2G. The reaction is reversed. Then what will be the equilibrium constant? Say equilibrium constant Kc is equal to, Krishna, can you help me? Krishna, can you help me? Can you give the equilibrium constant for the second reaction? Anna? Anna?
Yes, sir.
Can you help me?
Concentration H2 into
The concentration of H2 raised to the power 1 into, where there is plus, you put into concentration of I2 raised to the power 1 by concentration of HI, and the coefficient, number of moles is equal to 2 squared. Is equal to squared. Now you compare these two values. Is there any relation between these two? Any relation between these two? You call this as K dash. K dash. K dash C. Equilibrium constant for the reverse reaction. You call it as K dash C. H2 into I2 by HI squared. Can you find any relation between these two? Achyut? Any relation is there between these two?
Sir. Yes, sir. Yes, sir.
I can't hear you. Say the relation is this. K, say, dash is equal to 1 by Kc. 1 by Kc. Is it not? When the reaction is reversed, when the reaction is reversed, the equilibrium constant will be the inverse of the former one. The reciprocal of the former one. Is it not? See here. See, Hi squared by H2 into I2. And when the reaction is reversed, the equilibrium constant, that is also the inverse, the reciprocal of the first one. Reciprocal of the first one. So K dash is equal to 1 by Kc, or Kc is equal to 1 by K dash C. Kc is equal to 1 by K dash C, or K dash C is equal to 1 by Kc. So in this case, what will be K dash C? Kc is 57. Kc is 57. So what will be K dash C? That will be 1 by 57. 1 by 57. That is the equilibrium constant for the reverse reaction. Okay. So whenever the reaction is reversed, the equilibrium constant will be the inverse, the reciprocal of the first one, the former one. To make this clear, I shall take one more example. Say N2G plus 3H2G reversibly giving 2NH3G. Remember, we need all these things for the second year. You must be able to write the equilibrium constant in the second year. You have to apply this. So you must study it here itself. So what will be the equilibrium constant for this reaction? How can we get it? We can write it. Equilibrium constant Kc is equal to, anybody can say? Dia, can you say? Equilibrium constant for this reaction. Dia, you look at this equation and say
NH3, concentration of NH3.
Can't hear. Say concentration of NH3 raised up squared by concentration of N2 raised to 1 into concentration of H2 raised to the power 3, coefficient 3. So that is the equilibrium constant equation. See? And this relation is called the equilibrium law. That is the ratio between the concentrations of the products and the reactants is a constant. And that is known as the equilibrium law, or the law of equilibrium. I simply said it, that's all mentioned. So you must know how to write the equilibrium constant for this reaction. That's all. Let me give you another reaction. Say Fe plus 3 ferric ion plus SCN minus 1, reversibly giving Fe SCN plus 2. Say you are given an ionic equation. That is an ionic equation. The first one, molecular equation. The last one given here, ionic equation. In that equation, ions are involved. Fe plus 3 ion, SCN minus, that is a thiocyanate ion, and Fe SCN plus 2, that is a ferric thiocyanate ion. Then what will be the equilibrium constant for this? Equilibrium constant Kc is equal to concentration of Fe SCN S plus 2. Only one ion is there, divided by concentration of Fe plus 3. Only one ion. Into, wherever there is plus, you write into. Then concentration of SCN minus 1. Only one ion is there. And that is the relation for the equilibrium constant of this ionic equation. This equation is a ionic equation. Okay. So equilibrium constant Kc is the ratio between the concentrations of the products and the reactants. That is the equilibrium constant Kc. Suppose we have a gaseous reaction, then instead of Kc, we will get another equilibrium constant Kp. Instead of the concentration, you write the partial pressures of the reactants and the products and reactants. Then the equilibrium constant is called Kp. So Kp has significance when there is reactions involving gases. Say, for example, you take N2G plus 3H2G, reversibly giving 2NH3G. Here, the equilibrium constant Kc is equal to, concentration of ammonia squared by concentration of N2 into concentration of H2 raised to the power 3. That is Kc. But instead of the concentration terms, you can write the partial pressures of the products and the reactants. Instead of a concentration, you use the pressure of each species. So instead of a concentration of ammonia, you write partial pressure of ammonia. Partial pressure of ammonia squared by partial pressure of nitrogen into partial pressure of hydrogen raised to the power of 3. The only change is this. Instead of the concentration terms, we are using the partial pressures. Then the equilibrium constant is known as Kp. P for partial pressure. So in the gas phase reactions, we can have two types of equilibrium constants, Kc and Kp. Kc, that is equilibrium constant in terms of concentration, while Kp, that is equilibrium constant in terms of the equilibrium constant Kp, that is in terms of
gases.
Partial pressures. We are using partial pressures of the respective species. Okay. Now there is a relation between Kp and Kc. Let us see that relation. The relation is this. Kp is equal to Kc into RT raised to delta N. RT raised to delta N. That is the relation between Kp and Kc. Kp is the equilibrium constant in terms of partial pressure, while Kc is the equilibrium constant in terms of concentration. R you know that is the gas constant. T is the absolute temperature. And what is delta N? Delta N is the difference in the number of moles of the gaseous products and reactants. So delta N is equal to number of moles of gaseous, remember gaseous products minus reactants. Only gaseous number of moles of gaseous products and reactants. You consider only gaseous products and reactants. There may be solids or liquids, so you need not to consider that one. You take the difference in the number of moles of gaseous products and gaseous reactants only, and that is delta N. It may be, sometimes it is 0, it may be a positive value, it may be a negative value even. So let us take for example H2G plus I2G reversibly giving 2HIG. You take up this reaction. And what is the relation between Kp and Kc of this one? You want to find out, see, this is a relation. So you have to find out the delta N. What is delta N here? Delta N is equal to number of moles of the gaseous products minus total number of moles of the gaseous reactants. Gaseous products, number of moles, 2. So 2 minus number of moles of the gaseous reactants, 1 hydrogen and 1 iodine. So 1 plus 1. And this is equal to 2 minus 2, that is equal to 0. Delta N is equal to 0. Therefore, Kp is equal to Kc into RT raised to delta N is equal to Kc into RT raised to 0. RT raised to 0 is equal to simple math, that is equal to 1. That is equal to 1. Any quantity raised to the power 0 is equal to 1. 1 raised to 0 is equal to 1. 100 raised to 0 is equal to 1. K raised to 0 is equal to 1. Anything raised to 0 is equal to 1. Therefore, K is equal to Kc for this reaction. That is, number of moles on both sides are equal. Number of moles on both sides are equal. Then Kp is equal to Kc. Let us take another example. Say 2SO2G plus O2G reversibly giving 2SO3G. Let us take the relation between Kp and Kc. You find out delta N first. Delta N is equal to number of moles on the right hand side, not simply number of moles on, number of gaseous products, gaseous. So SO3 is a gas. Number of moles 2. 2 minus then gaseous reactants on the left hand side. SO2 2 plus O2 1 is equal to 2 minus 3 is equal to minus 1. Delta N is equal to minus 1. Therefore, Kp is equal to Kc into RT raised to delta N is equal to minus 1. And that is the value. See, you can find out the value like this very easily. It's very simple. Let me take another example. N2G plus 3H2G reversibly giving 2NH3G. 2NH3G. This delta N. Delta N is equal to number of moles gaseous products on the right hand side. That is equal to 2 minus left hand side 1N2. So 1 plus 3H2G. 3 is equal to 2 minus. Sorry. It is a 2 minus 4. That is equal to minus 2. And therefore, K is equal to Kc into RT raised to minus 2. And that is the relation between Kp and Kc. Okay. So we can find out the relation between Kp and Kc. If it is so, you find out the relation between Kp and Kc in the following reaction. CaCO3, calcium carbonate solid, decomposes giving CaO, calcium oxide solid, plus carbon dioxide G. Carbon dioxide G. This you have studied in the 10th standard. Decomposition of limestone. Decomposition of limestone. Now you find out the relation between Kp and Kc. Find out the relation between Kp and Kc. Find out the relation between Kp and Kc. Find out. It is time. Oh, it's only getting time. So what is the relation? Yes. Got it? So what is the value for this? K is equal to Kc into yes. What is RT raised to delta N. Delta N is equal to 1. Is it not? But there is a rule for solids. For solids, the concentrations are taken as unity. And here you have the value of, say, Kp like this. Kp. What is Kp? To find out the Kp of this reaction. Find out the Kp of this reaction. Kp, the product of partial pressures of the products by partial pressures of the reactants. So, product right hand side, partial pressure of calcium oxide, there is no meaning. Solid, you consider only the gas. So, partial pressure of CO2. Then, by, there is no by, it is solid. Solid. So, Kp is equal to partial pressure of carbon dioxide. Partial pressure of carbon dioxide. That is the relation. Kp is equal to partial pressure of carbon dioxide in that reaction. One thing more, let me mention about that. That is okay. Okay, friends, it is time. Let me stop now.